So today we're going to be looking at limits of complex valued functions, and the function we're going to be looking at is a fairly simple one, z over conjugate of z, and we want to find the limit as z approaches 0. We want to find what that is. Just a quick word on a difference between the limits of complex and real valued functions. Let's just have a quick look here. Let's just draw a little bit of a line here where this is the real and this is the imaginary. If we were looking for the limit as x approached x0, this limit here, real, it can only either approach from the right or the left. The limit from the right or from the left must be the same in order for the limit x0, x approach x to be equals x0 to exist. For a complex number, it is more complicated, far more complicated, because there aren't only two directions that you have to get the limit from. There are an infinite number of directions. It can come from any direction whatsoever, and regardless of the direction that you come from, the limit must be the same, otherwise the limit doesn't exist. And as we're going to see, the limit here does not exist because dependent on the direction from which you come, the limit is different. Okay, so let's have a look at the question at hand. So we have that the limit as z approaches 0 of z over the conjugate of z, well, that equals the limit as z approaches 0 of x plus iy over x minus iy. That's by definition of a complex number and by the conjugate. Now let's have a quick look here. First of all, let us approach along the real line here. Okay, now if we're approaching along the real line here, then by definition the imaginary part is 0, so y is equal to 0, and so therefore our limit simplifies to the limit as z approaches 0 of x over x, because iy is 0, because we're approaching along the real line, which is 1. So our limit is 1. Okay, well what about now? Let's have a look. We got our limit z approaches 0 of x plus iy over x minus iy. What about now if we approach along the imaginary line here down to 0? Well, if we approach along the imaginary line, then by definition x is 0, so that becomes equal to the limit as z approaches 0 of iy over minus iy, which is minus 1. And hey presto, with only looking at two approaches, along the real line or along the imaginary line, we have already found that the limit z over z conjugate does not approach the same thing. Therefore, we know that there is no limit because it has to approach the same value from all directions in order to there be a limit, and we've already found just after two that there isn't one. But anyway, let's carry on because it gets quite interesting here. So let's have a look. Let's approach from some other paths. Let's approach from this path here. Let's approach from the path a 1 plus I, where this is obviously pi over 4. That angle is pi over 4, and we're approaching from this angle here. Well, what is the limit then? Let's have a look. So we got the limit as z approaches 0 of z over z conjugate, which is equal to, well, if it's a 1 plus I, that's a 1 plus I over its conjugate, which is a 1 minus I, and that equals the limit of 1 plus I squared over 1 minus I 1 plus I, just multiplying top and bottom by 1 plus I to get rid of the conjugate, and that equals the limit as z approaches 0, as z approaches 0 of 2i over 2, which equals I. So we've now found a third value to which this converges depending on where we approach. So if we approach from the real, it was 1. If we approach from the imaginary, it was minus 1. And if we approach from the line a 1 plus I, it goes I as the answer. Okay, now what about if it comes from this line here? I won't bother drawing it. If it comes from this, well, that is a minus 1 minus I. Well, clearly if we put a minus 1 minus I, so let's just do that. That would be the limit as z approaches 0 of a minus 1 minus I over minus 1 plus I, and this is actually identical to that. So therefore we know that the limit, if we approach from this direction as well, also equals I. Okay, well, let's just carry on a little bit more. Let's have a look. How about if we approach it from here? A minus 1 plus I. Okay, well, let's have a look. Okay, so if we approach from there, then we have the limit as z approaches 0. Here's our point 0 here of z over z conjugate is equal to the limit as z approaches 0 of a minus 1 add I over its conjugate, which by definition a minus 1 minus I, and then just multiplying by the conjugate at the bottom, that gives us, the limit as z approaches 0 of 1 minus I over 1 plus I, 1 minus I, which is minus 2I over 2, which is minus I. So now we've got yet another value, this time coming from here. So when we came from the real towards 0, we got 1. When we came from the imaginary towards 0, we got minus 1. When we came from this line here, we got I, and now we're coming from this line here, we're getting minus I. And exactly the same, if we came from this line here, we would also get minus I. It's exactly the same calculation. Now finally we're going to do one more, and then we're going to give a more general form of this. So let's just have a look at one more. We are going to approach from the angle pi over 6 here. We're going to approach in from there. So this would be a root 3 plus I. Where does it go to if we approach from there? So okay, so let's have a look. We have our limit as z approaches 0 of z over z conjugate. In this case, approaching from here gives us the limit z approaches 0 of a root 3 add I over a, its conjugate, root 3 minus I, which is the limit as z approaches 0 of root 3 plus I squared over root 3 minus I, root 3 plus I, and that simplifies to a half 1 add root 3 I. So we have yet another value to which it converges when we go down this path here. Now we have enough information here that we can basically start generalizing, and the way to generalize is we put it in polar form. So let's have a look at our limit as z approaches 0 of z over z conjugate, writing it as in polar form, which is the limit as z approaches 0 of r e to the I theta over the conjugate, which by definition is r e to the minus I theta. The r cancels, and that gives us e to the 2I theta, which is equal to cos of 2 theta add I sine 2 theta. So basically what has been happening is that depending on where we have come from, let's see if I can draw this circle here. Oh, that's not bad, good. Okay, I managed to draw a circle properly. Depending on what angle we come in from towards 0, z over z conjugate ends up landing somewhere on the unit circle. So basically, and the way that we know where it's going to land is using this e to the 2I theta. So when we came in from theta equals 0, we ended up at 1, which again, cos of 2 times 0 is still 0. And when we came in from theta equals pi, we also found, because cos of 2 pi is equal to 1, so we also found that our limit was 1. When we came in from theta equals pi over 2, i.e. along the imaginary, well, pi over 2 times 2 is pi, and that's why we ended up at minus 1, and ditto when we came up from here. And when we came in from this angle here, pi over 4, which was a 1 plus I, well, cos 2 theta, e to the 2I theta gives us pi over 2, which means we are going to end up here, and ditto when we came in from this angle here, that there is 5 pi over 4, so it would be 10 pi over 4, which again is here, and that's why we ended up at I. Ditto when we came in from this angle and this angle, we ended up at minus I. And finally, when we came in from this angle, the pi over 6, when we came in from pi over 6, we ended up at pi over 3. But at each point, we are on the unit circle. And so basically, what we can say to conclude is that basically wherever the theta approaches from, we end up with a limit of, on the unit circle, of twice the angle that we came in. And there are an infinite number. Basically, all the way around the unit circle, you can find an approach, an angle approach, which will end up with the limit being at any point on the unit circle. Now finally, just before we finish, somebody did ask a question, why can't we use L'Hopital? And that is a good question. So if we look at the limit as z approaches 0 of z over z conjugate. You might think that we might be able to say, well, hang on a sec, that is equal to 0 over 0, so we can use L'Hopital and we can somehow differentiate this and differentiate that, and gives us 1 over 1, so the limit is 1. Well, you can't do that. And the reason why you can't do that is because z conjugate is not complex differentiable. And it has to be complex differentiable in order for us to be able to use L'Hopital, and that's why you can't use L'Hopital. Okay, well, I hope you found this useful and informative, and it's enlightened you as to the ways of complex limits. If it has, then please like this video and subscribe to the Gresty Academy YouTube channel. Thank you.